Hello everyone, and welcome to our ME260 Applied Stress Analysis presentation. Today we will be discussing unsymmetrical bending of a floor beam. This presentation will include an introduction, theoretical analysis, FEA, as well as a comparison of the two. The C-beam selected for this analysis is a supporting structure of the floor for an aircraft or spacecraft. It is currently used in the aerospace industry as indicated in the lower left image. The spacecraft selected is expected to carry a maximum payload of 55,250 pounds. The region focused for this analysis will be the payload bay or the cargo bay. It has a size of 60 feet long, 17 feet wide, and 13 feet high. This is depicted in the lower right corner. Only 15 feet, however, will be used to carry the dry cargo. The selected C-sectional beam is positioned so that it experiences an unsymmetrical loading. This is presented via the 3D view below. The loading is expected to be along this top area of the beam. In the theoretical 2D view, the loading is depicted as a distributed load over a simply supported beam. The overall length of the beam is expected to be 3 feet and is made out of structural steel. In the spacecraft, the cargo bay is supported by 12 main vertical frame assemblies. This is shown in the sectional views below. It will carry about 2,050 newtons of uniformly distributed load. The selected beam for this analysis is manufactured by the Hadley Group. The dimensions for this beam are shown within the highlighted region. In loading of beams with unsymmetrical cross-sections, the same equations and theories for the symmetrical cross-sectional beams may be used. The equation for stress in the x direction is the following, where the bending of stress along the particular axes. The only difference in the unsymmetrical cross-sectional beams case is the second area of moment, IY and IZ. In the case of beams with symmetrical cross-sections, the second area of moment is expected to equal to 0. But this is not the case for unsymmetrical cross-sectional beams, for they generally have non-zero second area of moment. In this case, we find a new coordinate system rotated at an angle theta, about the x-axis, to the principal coordinate system. This can be obtained by using the following equation. After obtaining theta, the rotation matrix and the transformations can be used to find the moments of inertia in the new principal plane. The rotation matrix for rotation about the x-axis is the following. Moments too are converted to this new coordinate system. Next, the equation is applied to find stress, and this obtained value is then reported to the new principal coordinate system. In our initial assumption, the uniformly distributed load will be about 2,050 newtons. Fortunately, in our case, the second area of moment is 0, so we can go as per the symmetrical beam analysis. The only difference will be the method to calculate area moment of inertia. The moment about the y-axis will be 0, because we are only finding the maximum bending stress in the x direction. The following parameters have their values. Thus, we find that sigma x will be 45.91 megapascals, and sigma x as a function of load applied will be the following. The boundary conditions for the FEA is shown in the following image. The bottom edge of the left side is fixed, and the bottom edge of the right side has a displacement in the z direction. The beam is loaded with about 2,050 newtons, uniformly over the top flange. The evaluated values are the normal stress in the z direction, x in the theoretical analysis case, deformation, and normal elastic strain in the z direction. The normal stress in the z direction is shown in the figure of the color gradient, presented by the FEA results. Applying St. Venant's principle allows us to ignore the indicated maximum stress, which are at the supporting ends. The maximum stress occurs at the middle. Hence, we can see from the color gradient that the value is within the range of 40 to 50 megapascals, which is quite near to the theoretical value. Here we have the stress and deformations graphs. We have an overall value within this region. This is the total deformation. The maximum deformation is along this region. Here we have the graph of strain along the z-axis. The overall values are within this color gradient. For the experimental validation plan, we'll be using a strain gauge, which will be attached at the bottom center of the beam using adhesive. The beam, 3 feet long, is placed on the support pillars, depicting the vertical struts. Measurements from strain gauge before loading will be taken. Load will be added on the top of the beam. Measurement at the end of each loading will be taken. The strain values for different loading will be plotted against load applied and compared with theoretical value and the FEA simulations. The graph of strain versus load depicts the theoretical and FEA results. A linear variation in both cases is observed. Percentage difference between the two results is about 13%. The stress increases linearly as the load increases in both cases. The difference may be due to the assumptions made for the theoretical calculations. FEA results here can be considered more realistic, as it is a 3D analysis. In conclusion, the FEA results are in close agreement with the theoretical results. The stress values found are below yield strength of 220 megapascals with a factor of safety of 2. It is seen that the selected beam can take double the load than it is designed for, while the factor of safety remain greater than or equal to throughout. Here is our body of references. Thank you for listening.